In this video, I'm going to start our discussion about probability. So the first thing to look at is what is randomness. And so there are essentially two different definitions of randomness. And so the first one here is a lack of patterning in data. And so that's kind of what we can see over here with this image of static is there's no pattern in this data. I mean, humans have kind of a tendency to find patterns even in noise. And so, you know, somebody might be able to sort of convince themselves they see something there, but there is no pattern to that data. It's just absolute noise. And so, Steven Pinker says in his book about rationality, a data set is non-random when its shortest possible description is shorter than the data set itself. And so we see that these six nines here, so 999,999, is equal to, so we can just say six nines, and so that description is shorter than the actual data set itself. Whereas if we have 634,579, this must be stated verbatim, so there's no description of it that's actually shorter than the data set itself. It's just if you want to describe this number, this data here, then you just have to name off the data. And so the other definition of randomness is a lack of predictability in a process. And so, uh, so Steven Pinker actually has this comic in his book, so I found it again online. And so there's the tour of accountants where Dilbert here is being led through. It looks like it's probably hell. So over here we have a random number generator, and this guy is just saying 9 over and over again. So he asks, "Are you sure if that's random?" No, that's the problem with randomness. You can never be sure. And so the idea being that, you know, even if this guy is sitting here saying 9 over and over again, you don't know what the next number is actually going to be. You know, at any time he could suddenly say some other number. And so getting six nines in a row would be expected if a process is truly random and is allowed to run long enough. So I actually put this example here where the digits of pi, which are oftentimes thought to be sort of random, because the whole thing about how it never repeats. And when somebody says they never repeat, they mean that you wouldn't get like this block of numbers here after the decimal point, and then suddenly just repeat this whole block starting, at the end here. So there's no repeat in the sense of, if you have, say, the number, say we have like 3.175392, and then we start again 175392, and then sort of keep repeating that over and over again. So when they say it never repeats, what they're talking about is it never gets to a point, there never comes to a point where suddenly the previous sort of block of letters, or numbers rather, however long that might be, starts repeating itself. And so we do see, these sort of consecutive repeats in pi. And in fact, we actually see six nines here in pi. And you can see there's these other places where we have some of these shorter repeats. And so even in something that's thought to be sort of random like pi, we do end up seeing these repeats like this. And so Steven Pinker doesn't go into this in his book, but I thought it was kind of interesting. So how random number generators actually work. So this is from Wikipedia. So there's two principal methods to generate random numbers. And so this first one, which is talked about up here, is essentially using natural processes like atmospheric noise or thermal noise or things like that. So sort of entropic things that are sort of, uh, you know, intrinsically noisy. And then the second one here is using these computational algorithms that are called pseudo-random number generators. And so they're pseudo-random because if you if you know what the sort of initial condition is, you could regenerate the random number sort of completely just by knowing what's called the seed here. And so that's sort of the initial condition. Uh, and I mean, if you think about it, something like atmospheric noise would itself be sort of pseudo-random because if you knew down to perfection sort of what all the molecules in the atmosphere were actually doing and sort of knew their exact positions and momenta, then you could sort of predict what the atmosphere is going to do. So it's just a extremely complex system, and so we are sort of ignorant of it. And you could probably get into uh, sort of quantum effects and stuff like that, which are intrinsically random or irreducibly random, rather. But that's kind of a whole other topic. So this pseudo random number generator uses an algorithm which is actually itself deterministic. So you see in this image here, it even says deterministic. And so this linear congruential generator here is one that you would often find. And so this mod M here is just telling you that essentially that we're thinking of like a circle of numbers. And so if you want a random number like between 1 and 100, you would want like a mod 100 so that you don't actually go over 100. If your algorithm after it gets to 100, then once it goes over 100, it kind of goes back to 1. So you can think of like a clock. A clock is modulo 12. So, if you start at 12 and then you go around the clock, and once you get back to 12, then it sort of starts over. And so that's kind of what the modulus means in this instance. So I'm not going to go through this algorithm and go through what it means, but I just wanted to kind of point out that these random number generators are actually pseudo random number generators because they are actually deterministic. All right, so let's get to probability, which is, sort of a way of thinking about randomness. And so we have here, so probability is the uncertainty of outcome. So you're about to perform a task and you don't know what the outcome is going to be. We can assign probabilities to it. And so here I put irreducible uncertainty would be something like a quantum event. And so this here isn't in Steven Pinker's book. This is sort of my kind of working definitions here. And then so the other one would be something that I call chaotic uncertainty, which would be things like the butterfly effect. And so we think about rolling dice. So minute changes in forces on the dice can have large effects on the outcome, but how it will land is in principle deterministic. In fact, I think there are people who have sort of built robots that can actually 100% of the time get the right coin flip. So if you want heads 100% of the time, you can get heads 100% of the time using these robots that can control these minute forces to the point where you can get 100% heads on your coin flip. And so this also is not in Steven Pinker's book. So information theory, which is something I find very interesting. And in the future, I might make a playlist on information theory. But we can think of information broadly as the reduction of uncertainty. And so, say I roll a die behind a barrier. Say I'm like the dungeon master, and I'm rolling my dice behind a barrier, and it lands on a number. You don't know what that number is, but then once I announce it, then you know what the number is. And so, say I'm rolling my d6, and the uncertainty is reduced from 1/6 to 1, and so this gives information. So the uncertainty was 1/6 until I announced what I actually had. Then you had 100% certainty. And so in information theory, there are actually ways to calculate sort of the bits of information using this reduction in uncertainty. All right, so Steven Pinker goes through 5 definitions or interpretations of probability. And so there is the classical definition, which is the number of ways a specific event can happen divided by the number of all possibilities. So if we assume a fair 6-sided die, so the number of ways a die can be even is 3. So if it's 2, if it's 4, or if it's 6, then it's even. But the number of possible ways that the die can land is 6. So, a 6-sided die has 1 through 6. So the probability of getting an even roll is 3 out of 6, which we can simplify to 1/2 or 0.5. So 0.5, if you times that by 100, 50%. So a 0.5 probability of getting an even number when you roll a fair 6-sided die. And then so there is also propensity, which is the interpretation that the die has an equal chance of landing on each side. Once again, assuming a fair 6-sided die here. So the die has the same propensity to land with 6 showing as it does with 5, which is the same in the as 4, 3, 2, or 1. So each side is the same propensity. Whereas if you have a weighted die, so an unfair die, you could put a greater propensity on some of the numbers than on the others. So say it's weighted so that 6 shows up more, then there would be a greater propensity of 6, than say 1 or 3 or something like that. Then we have the subjectivist interpretation. So that's just what a person's guess is. And so this is kind of that idea that I talked about before, that we can put sort of a number on our ignorance. And so based on everything you know, how would you quantify between 0 and 1 your belief that the die will land even? So how would you put a percentage on a single event? And so this is kind of one of those things in probability theory about, what does it mean to put a probability on a single event? And so Steven Pinker uses the example of what is the percent chance that you were older than 50 years, so that you were more than 50 years old. And so this sounds absurd because you're either over 50 or you're not. But before I know what the answer is, I could put a number on my ignorance. I mean, if I'm completely ignorant about it, then I might want to use sort of the base rate of the fact that, most people are going to be sort of, uh, you know, under 50 because, before you get to 50, there are sort of ways that you could, stop aging before you get to 50. Or anyway, I'm not going to go too far down that rabbit hole. I'll get into base rates and things like that in one of the upcoming videos. So then there is the evidential interpretation, so the degree to which you believe the information presented warrants the conclusion. So this is things like you would see like confidence intervals in statistics, or the, p greater. Actually, I should have put this as less than. In science, you want it to be less than 0.05. So that's the standard in science. And so there's this example that Steven Pinker talks about, but he doesn't actually end up going into detail about the probability of precipitation in weather predictions. So I wanted to kind of give a more in-depth look at this. And so the probability of precipitation, which is POP, or what I'm just going to call P, is determined by this formula here. And so C is the confidence, or the degree of belief the weather model warrants the conclusion that it will rain. And so that is sort of our evidential interpretation there. Then there's A, which is the percentage of area that will receive a measurable precipitation. And then so if the weather forecaster says they are 90% sure that 70% of the region they cover, which, if you watch the weather, that's that sort of geographical area that they show on their map, will receive some measure of rain. Uh, then what they have is P equals C times A, or the 0.9 from the 90%, then the 0.7 from the 70%, which is 0.6. And so when you hear the weather forecasters say there is a 60% chance of rain, what they're saying is that, if they're looking at their map, so they're looking at the region that they cover here, they're saying that there is that 70% of the region they cover, and so maybe we could sort of block this off here. That's 70% of the region they cover. There is a 90% chance, so a 90% chance that 70% of the region they cover will receive, some measure of rain. And so that's one of those things that I think is oftentimes not well understood by the general public, what it means when the weather forecaster says there is a 60% chance of rain, is that you have to take into consideration this confidence, or the evidential interpretation, and sort of the region that they're actually talking about, sort of the region that a certain weather forecaster actually covers. And then probably the sort of most intuitive interpretation is the frequentist interpretation. And so that's, if you roll a die many times, say 1,000 times, then it will be, then the number will be even about 500 of those times. Or, in sort of political forecasting, say there is a 70% chance that A wins and a 30% chance that B wins. So some pollster is telling you that there is a 70% chance that candidate A wins and a 30% chance that candidate B wins. So in the frequentist interpretation, we would say that if the election was run 100 times, then candidate A would win 70 of those times, and candidate B would win 30 of those times. So that's probably one of the more sort of intuitive interpretations of probability. But like I said, there are these 5 of them here. So we have the classical definition, which, I think that's, somewhat intuitive as well, but it's still kind of putting a percentage on like a single event. But we have the classical definition, we have the propensity definition or interpretation, we have the subjectivist interpretation, the evidential interpretation. And so the subjectivist and the evidential are fairly similar to me, because in both cases we're kind of trying to put a number on some uncertain outcome based on information that we know. But I don't know, maybe the evidential one is a bit more objective than the subjectivist one. But then we also have the frequentist interpretation. And so, yeah, that is the sort of introduction here to probability. In the next few videos, I'll actually be sort of giving definitions of probability in things like conjunctions and disjunctions and complements, and then sort of the big one, which is conditional probabilities, which is probably one of the ones that people have the most trouble with. And I'll show some examples of where people go wrong with conditional probabilities. But anyway, I hope you found this video helpful, and I will see you in the next one.